Okay, welcome to part 2 of topic 4, which is nuclear structure and radioactive decay. And in this second part, we're going to look at some questions that have appeared on past public exams that are related to the different types of radioactive decay and to the topic of the structure of the nucleus. So without further ado, let's go and get started. So the first question says, which would complete that nuclear decay reaction shown? And you'll notice that the only thing that shows over on the other side over here is this, and that's the symbol for gamma. And remember, in gamma radiation, the only change is energy of the nucleus. There's no numbers associated with this gamma radiation. It's actually 0, 0, just like a neutrino. So that means that the numbers are going to stay the same, 5829. So the only one that stays 5829 is D. So that would be 5829 copper. In other words, it doesn't really change. All that happens is it becomes a lower energy version of the same nucleus. That's it. It emitted a gamma photon. All right, let's look at the next one. An atom that has 98 protons and 249 neutrons undergoes alpha decay. What will be the numbers of protons and neutrons in the daughter nucleus? Well, let's just concentrate on protons. Remember that an alpha particle is 42He, your helium nucleus. This bottom number right here, the 2, that tells us the number of protons that have been emitted. And the top number tells us the number of protons and neutrons. So 4 in total. But 2 of them are protons. So if we lose 2 protons, what we have is, originally we had 98. If I take away 2, I'm left with 96 protons. Only one of the choices there has 96 protons. I don't even need to worry about the number of neutrons. But if I did need to know the number of neutrons, it also loses 2 neutrons, so there's also 249 take away 2. Which is 247 neutrons. But like I said, I didn't need to worry about that because the number of protons did it. Solve the question. Because it was the only choice there that had 96 protons. Okay, so moving on. Which isotope is produced when this one, 21483Bi, decays by emitting an alpha particle? So there's the alpha again, 42 helium. What that tells us is that the top number, we have to subtract 4, so it's 214 take away 4, which is 210. So there's 2 choices there though like that. So now we got to look at the bottom number 2, which is going to be 83 take away 2, which is 81. So 210 and 81, it's got to be this one. And the atomic symbol really doesn't matter. It's only the numbers that you're going to be worrying about. You have no way of looking up that atomic symbol unless you got it memorized in your head. You have no way of knowing that. No way at all. Let's take a look at the next one, which describes the atomic number and the mass number for a nucleus that just emitted a beta particle. Well, remember, when we emit a beta particle, when you emit a beta negative, okay, when you emit a beta negative, what happens is you gain a neutron. Okay, a beta negative emission, our nucleus gains a neutron because what happens is a proton, oh, hold on, now I got that backwards, gains a proton because a neutron breaks down to give us a proton. Sorry about that. Let's fix that right quick. For beta negative, we gain a proton, not a neutron. We gain a proton because what happens is a neutron decays into a proton and releases that electron. So we gain a proton, but in a beta positive, we lose a proton. It's the opposite. We lose a proton, but we gain a neutron in the process. So in other words, the atomic number, regardless if it's a beta negative or a beta positive, is going to change. So the atomic number changes. It either goes up one or down one. We don't know which, but it doesn't matter, because all it says is the atomic number changes. So it could be this, it could be this. So we know it's not C or D. We've got those two eliminated right away. What about the mass number? Well, remember, in a beta negative, when we gain that proton, we lose a neutron in the process. So that tells us that the total number of nucleons is constant, because by gaining a proton, we lose a neutron. And in the beta positive, by losing a proton, we gain a neutron. Okay, so we lose one, but we gain the other. So it is constant, in other words. It's constant. So the answer is B. Now, that's a tough one. That's kind of a level 3 question almost. Okay, you really got to think about that one. Let's move on. How many electrons are in that atom? Well, the bottom number there tells us there are 3 protons. But remember, in an atom, which is neutral, 3 protons means 3 electrons as well. Now there's also 7 minus 3, which is 4 neutrons. We're not asked for that, but that would be the number if you were. So there are 3 electrons. Okay, that's the right number. Next question. A beta positive particle is emitted from an unstable nucleus. What happens to the atomic number of the nucleus? Remember, for a beta positive, what happens is this. A proton decays into a neutron. A proton decays into a neutron. So what that means is we lose a proton. We lose a proton, but we gain a neutron. Lose a proton, gain a neutron. But the lose a proton is the important part for the atomic number, because the atomic number is the number of protons. So if we lose a proton, that means the atomic number will decrease by 1. It will decrease by 1. If that were a beta negative, it would be the opposite. It would increase by 1. Anyway, complete the nuclear reaction. All you have to remember in these nuclear reactions is that every single time the numbers on each side have to be equal. So right here we've got 16 plus 1. That equals 17. Over here we've got question mark plus 4 also has to equal 17. So that tells us that the question mark on top must be 13, because 13 plus 4 would be 17. So I know it's either this one or this one, because those are the ones that have the 13 on top. Now we got to figure out which one is right. So I do the same thing on the bottom. 8 plus 0, I add the bottom numbers, which is 8. So question mark plus 2 also has to equal 8. So that question mark, that unknown, must be 6, because 6 plus 2 equals 8. So now I know the numbers are 13 and 6. It has to be that one right there. It has to be B. There's no other option. Okay, and that's the way you do it. Balance the numbers, almost like balancing equations in chemistry, only easier. Let's try this one. What type of decay is that? Well, there's the magic one right there. You know what that symbol is? That is an alpha particle. And the symbol for alpha is that one there. The one that's the same as the proportionality sign in mathematics, or in physics for that matter. The next one, how many neutrons are in that? Well, remember, to get the number of neutrons, you just take the top number and subtract the bottom number. That equals 123. So the correct answer is B. Okay, pretty straightforward. Then the bottom one there says, what type of nuclear radiation will go straight through a magnetic field? Right on through. Doesn't get deflected. If it doesn't get deflected, that means it has no charge. The only one there that has no charge, this one's a positive charge, this one's a negative charge, this one's a positive charge, this one is zero charge. That one is neutral. That's the one that goes straight through them. The other three would get deflected as they went through the magnetic field, because charged particles experience a force when they go through a magnetic field. You learned that in Unit 2. Let's try this one. Alpha decay again. Now this time there's no numbers, but you got to remember that the alpha is a 4-2 helium. So what you're looking for is numbers have the balance. In other words, if I put a 4 here on top, what's 227 plus 4? That would equal 231. That's not the number on the other side, so I know that's not the right answer. And again, if I put a 4 on top and a 2 on the bottom, right, 228 plus 4, that would equal 232. Again, not the number on top. No good. The next one, 228 plus 4 would equal 232 again. It's not that one. Well, there's only one left now. Let's just double check it to be sure. 224 plus 4 equals 228. So the top is good. And on the bottom, 88 plus 2, that would equal 90. Those are the numbers on the other side, so that is the right answer. But you got to look for the balanced numbers. The numbers have to balance. Okay, next one. An element with an atomic number of 88 goes through beta negative decay. Now remember, in a beta negative decay, a neutron decays into a proton. You got to try to remember that. A neutron decays into a proton and releases that electron in the process. So in other words, we gain a neutron, but by gaining a neutron, we lose a proton. That's the process. Gain a neutron, lose a proton. So that means if we lose a proton, I've got 88 minus 1. So the atomic number would now be 87. Goes down to 87. Keep that in mind. You need to know what these different decays are. The alpha, the beta positive, the beta negative. You have to know what's happening, because you would have to be prepared to answer these types of questions, because they do show up fairly often. Let's try this one. This one is the one that's all about the particles being deflected. So we got 3 different types of radiation that are being affected by a magnetic field. So obviously, the one that goes straight through, we know right away, the one that goes straight through is the gamma, because the gamma has no charge. So that means beam 2 is gamma. So that means it's either A it's either B or D. So we can cancel out A and C right away, because we know it has to be gamma. All right, now let's use our left-hand rule to see which one of these. Let's see which one of these is a beta negative. Let's see which one of these has a negative charge. Those X's for the magnetic field show the magnetic field going into your screen. So I point my fingers into the screen. I point my thumb towards the top of the screen, because that's the direction the particles are initially moving in. And when I do that, my palm points to the right. My palm points to the right. So for your left-hand rule, you get your palm showing a force this way. That force would act on the negative particle. So the negative particle, got to be that guy right there. Beam 3 is the beta negative. So therefore, the right answer must be B. Beam 3 has to be the beta. Now it doesn't say beta positive or beta negative, but we know it's got to be beta negative because it goes in the opposite direction of the other one. So we know it's a beta negative. So there's the answer. Got to be B. Things similar to that, by the way, have shown up a couple of times on Old Public, so you really should be ready for that. How many protons, neutrons, and nucleons are in this nucleus? Well, the nucleons, remember, that's the top number. So the nucleons is 45. So it's either this answer or this answer. We can cross these two out right away. How many protons? Well, the protons, that's the bottom number. That's the protons, because that's the atomic number. And that means the protons is 20. So there you go. That's the only one that's possible. That's the only one that's possible. And the number of neutrons obviously is 45 take away 20, which is 25 neutrons. Now, this last one here, this is a fairly obscure fact, but it doesn't hurt to know it. The radioactive emission that has the greatest penetrating power is gamma. Gamma has the highest penetrating power because it has the most energy. Gamma is very high energy particles. They also have no mass, so they can go right through. In fact, gamma particles go right through the Earth. Okay, they go right through your body without even slowing down. They're so high energy. Okay, but they're not terribly harmful. Alpha are actually more dangerous in that way than gamma, because alpha have very little penetrating power, but because they're so massive, they have a lot of ionizing ability. And ionizing ability means they have the ability to strip electrons away from atoms. And that can be dangerous in some ways. But anyway, the gamma has the most penetrating power. The alpha has the greatest ionizing ability. So that's another thing that doesn't hurt to know. Alpha has the greatest ionizing ability. Okay, and the betas are somewhere in between. Next question. Which one of those transmutations is alpha decay? Well, again, you've got to look for the alpha. You look for the alpha. Now, there's two here that have an alpha particle, isn't there? Those two. But only one of them is written correctly. Only one of them is written correctly. And that would be B, because you look at the numbers, right? 226 plus 4 is 230. Right here, 227 plus 4 will be 231. So that eliminates that one. The numbers don't add up. Okay, which transmutation represented by that equation? Again, that particle is an alpha particle, so we've had that question before with a different reaction. You look at the particle. The particle tells you which type of decay it is, or which type of transmutation it is. Which one of those shows a beta minus decay? Well, only two of them show the proper symbol. The proper symbol for beta minus is 0, -1e. So this one has the wrong symbol, and this one has the wrong symbol. So it's either B or D. So now you've got to add up the numbers to make sure they work. Well, look at the 0. 0 on top means that the top number has to be 0 plus 90, which is 90, so that one works. This one down here, 0 plus 90 is 90. That one works too. But if we look at this one down here, the bottom numbers have to add up to 38. So look over here, -1 plus 37, that would equal 36, not 38. So because the numbers don't add up, that equation is wrong. There's only one left. -1 plus 39 does equal 38. So that one is good. That one is good. Let's look at the bottom one on the screen. Which one of those would complete that nuclear reaction? And again, don't worry about the atomic symbol. Worry about the numbers. Worry about the numbers. So let's look at what the numbers should be on top. On top we have 1 plus 235, which equals 236. So we have 141 plus, 141 that is, plus our question mark, plus these 3 neutrons means 3 more. You've got to be careful there. 3 times 1 also has to equal 236. So 141 plus 3 is 144. Okay, and 144 plus 92 would give me 236. So I know that question mark on top, it has to be a 92. So right away I can cross out B and D. B and D are gone. All right, so we've got either 9235 or 9236. Well, let's check it out. Look at the bottom numbers. 0 plus 92 equals 92. So the bottom numbers have to add up to 92. So I've got 56 plus my question mark plus 0 has to equal 92. That means that that bottom number has to be a 36. Therefore, it's this guy right here. It's krypton. Okay, but all you got to worry about is the numbers. Like I said, don't worry about the symbols. Symbols don't matter. Symbol doesn't matter. Just trust that that's right. Just look at the numbers. See what the numbers are. How many neutrons are in the daughter nucleus if this guy undergoes alpha decay? So let's see how many are there now. So right now, initially, there's this. Okay? And 235 minus 92 is 143. So there's 143 neutrons before. That's before. So the answer is not C. We want to know how many are there after. Well, remember that in an alpha decay, we lose 2 neutrons. 2 protons and 2 neutrons. So therefore, there are only going to be 141 left. That's an alpha decay. We lose 2 protons and 2 neutrons. That's our helium nucleus. Next one, what is the number of protons, neutrons, and electrons in this atom? Well, I know right away because the bottom number is 41. I know there's 41 protons. So that eliminates this answer right off the bat. But I also know there's 41 electrons because this is an atom, and atoms are neutral. So not only are there 41 protons, there are also 41 electrons. That's the only one that matches. We don't even need to worry about the number of neutrons again. And you can notice there, if you look at the number of neutrons, it was the same in every choice anyway, so obviously that one was not going to be the determining one. All right, what's missing in this reaction? Well, if you look at the numbers, the top number is supposed to be 234, so 230 plus 4 would equal that. Bottom number should be 90. 88 plus 2 would equal 90. That's a 4-2 helium, which is another way to write an alpha particle. So the alpha seems to come up a lot. Okay, that one's a very common question. Last couple. Which type of decay emits a helium nucleus? Like I said, I just took these off of all public exams. Okay, and this is obviously a very common question. The helium nucleus, that's alpha. That's alpha. Which best describes X in this reaction? Well, just look at the numbers. It would have to be a 4 on top and a 2 on the bottom. So in other words, the atomic number would have to be 2 and the mass number would have to be 4. That would be A. Those are the types of questions you see. I've never seen a question on part 2 related to this stuff. It's always in the multiple choice. In terms of nuclear structure and the radioactive decay reactions, it's always been on the multiple choice, not a part 2 question. That's why you see no part 2 questions there. There haven't been any. Now, will there ever be? Not likely, but you never know. They might come up with a question to ask about that doesn't require a periodic table, but most of the questions like that would require a periodic table if you didn't already have the symbols, for example. But if you're only worrying about numbers, that's going to be in the multiple choice. Okay, so that finishes up nuclear structure and types of decay. The next topic, topic 5, is going to be all about the rates of decay and half-life calculations. And many of you will have already done that in math, but some of you may not have, so we'll spend a little bit of time reviewing that. That's one calculation that there's a pretty safe bet it's going to show up. Not only that, most of the time when it does show up, it is the question that is graded for significant digits and units. So if you see a half-life calculation on part 2, chances are that's the one that's worth the extra mark. All right, so as I always say, good luck with your studies, work hard, and make sure you come back and view some more of these lessons.